The broadcast is now starting. All attendees are in listen-only mode.
All right, good morning or afternoon, everyone, wherever you may be. My name is Zach Imam. I'm a research scientist here at RheoSensense in San Ramon, California. And today I'll be adding some tools to your rheology toolbox on how to tame your non-Newtonian data with the Weissenberg-Rabinovich-Mooney correction, or WRM correction for short. So first off, we'll just answer a commonly asked question, which is what exactly is viscosity? It's a fluid's resistance to flow. It's caused by the fluid layers shearing against each other. And it's equivalent to the molecular friction. So it'll reflect the molecular level behavior of the fluid itself, the size and shape of anything suspended in the fluid and their interactions, and any microstructure in the fluid. And with regard to non-Newtonian fluids in particular, their viscosity is shear rate dependent. And so you can probe different lengths and time scales by changing the shear rate when you're doing your viscosity measurements. So over here on the right, I have an example of a homogeneous flow, which has a constant shear rate. So this slope here is the shear rate as a function of the velocity u in the x direction as it changes in the y direction. And so this shear rate is equal to the velocity of, in this case, the plate that is inducing the flow divided by the height of the gap in this example, which was kind of simulating a cone and plate rheometer. And so, like I said before, or may have not said before, but viscosity, eta, is equivalent to the shear stress exerted on the fluid divided by the shear rate that the fluid is experiencing. And so with that, I'd like to continue on some types of flows that we see when we're measuring viscosity on different rheometers and viscometers. So like I mentioned in the previous slide, certain rheometers can induce homogeneous flow, and that the most common example for that is the cone and plate rotational instruments. These instruments, because they have a homogeneous, non-changing shear rate across the entire fluid, these instruments don't require the WRM correction because the assumptions made by these instruments basically aren't broken when a non-Newtonian fluid is introduced. And on the right, we have an example of an inhomogeneous flow, which is in this example, it's a pressure-driven flow. So capillary tube or our system, microfluidic channel viscometers, will induce this sort of flow. And this type of flow isn't exclusive to microfluidic channels or capillary tubes, or inhomogeneous flows are not exclusive to these instruments. Parallel plate rheometers also induce inhomogeneous flow, just not in this exact shape. And so some of the assumptions that we make when we're measuring fluids on rheometers and viscometers are there's no slip at the boundary, that we induce a fully developed laminar flow, no turbulent flow, that the fluid itself, the sample itself, is homogeneous. And then specifically for inhomogeneous flows on our instruments, we assume that the shear rate, the change in shear stress divided by the change in shear rate is linear. So the next slide, we have a couple examples of how to calculate the shear rates for different rheometers. So on the left here, we have a parallel plate where omega is the angular velocity, and we have the gap height h, and then the 2r, 2 times radius of the parallel plate, and we can calculate the shear rate of this system by simply following this equation, gamma dot equal to the radius times the angular velocity, which we can control, divided by the gap height. And so you can see that you can influence the shear rate either by increasing the angular velocity or by decreasing the gap height. However, when you're decreasing the gap height, you must be careful. If you have any particles in your suspension, you need to make sure that the gap height is large enough to allow these particles to flow. And then over here on the right, we have an example of a cone and plate rheometer. Again, we can control the angular velocity omega here, but because of the angle of the cone, in this case beta, this changing angle across the entire radius of the plate is what creates the homogeneous flow exerted by the cone and plate instrument. And so we can calculate this shear rate, again, gamma dot equal to the angular velocity divided by the angle beta. So we can go over our instrumentation. So our instrumentation is a little bit different here at RheoSense. We use viscometer, rheometer on a chip, or VROC technology, where we have 4 pressure sensors, and we can measure the pressure drop as the fluid flows across these 4 pressure sensors. I guess I could be a little bit more specific. We're actually measuring the change in capacitance, which is correlated with a change in pressure across the 4 pressure sensors here. And with this pressure drop, we can then calculate the shear stress at the wall that the fluid is experiencing, because we know the dimensions of our rectangular channel here. And then in this way, we can control Q, which is flow rate. And when we do this, and then we can use this flow rate to calculate the shear rate based on the geometry of the chip itself. And so we can control, increase or decrease shear rate by increasing and decreasing flow rate. And in our instrument makes the assumption that the shear rate is Newtonian, or the fluid that is in the channel is Newtonian. And this is why we need to make the WRM correction with our data when we are using non-Newtonian, or when we are measuring non-Newtonian fluids. And so our instrument measures the shear stress, and we calculate the shear rate based on the flow rate we can control to get the apparent viscosity of the fluid. Again, this needs to be corrected when we experience or when we measure non-Newtonian fluids, and I'll explain why in a few minutes. And so what exactly is the difference between a non-Newtonian fluid and a Newtonian fluid? Simply put, a Newtonian fluid's viscosity does not change as you change shear rate. A non-Newtonian fluid's viscosity is shear rate dependent, and that is the key difference. And so on this graph here, we have shear rate and shear stress on the y-axis. And so as you can see with a Newtonian fluid, this shear stress over shear rate is linear. So as the shear rate increases, the shear stress increases linearly. However, with non-Newtonian fluids like pseudoplastics, which are shear thinning, as the shear rate increases, the shear stress changes non-linearly as the shear rate increases. And with shear thickening fluids, which are also known as dilatant fluids, we can see, again, as the shear rate increases, the shear stress changes non-linearly as well. So here we have a few examples of what is a non-Newtonian fluid and what is a Newtonian fluid. So some common Newtonian fluids we see here at RheoSense are obviously water, buffer with low molecular weight excipients or osmolytes, depends on your field, what you call those things. So sugar, polymers, what have you, organic solvents, mineral oils, and then extremely dilute, or not extremely, but dilute polymer solutions and colloidal suspensions are also Newtonian. And then some examples of non-Newtonian materials are more concentrated colloidal suspensions like protein solutions and microemulsions, some polymer melts, and then any system that has any form of structure or self-assembly, so like block copolymers, lotions like hand creams and soaps, or you're, washing your hair and stuff. So I want to point out that that these are basically the same solutions. It's just they shift from being non-Newtonian behavior to Newtonian in behavior as the concentration of the suspended particles increases. And this is in large part due to differences in particle size, Pauli dispersity, but also any interactions between the different particles in solution. The more interactions they have, the tighter they interact at low shear when they're undergoing low shear. But as you increase the shear rate, the shear stress and shear rate causes these breaks down these interactions that these molecules in suspicion have with each other. So just wanted to point out that it's not size but ability to interact that can influence the structure of your fluids. So looking more deeply at non-Newtonian behavior as to why we need to do the WRM correction, as I've stated before, the viscosity is no longer, the viscosity is completely dependent upon the shear rate that you induce on the fluid or impart on the fluid. And so when we make the Newtonian assumption in our channel, we're assuming a more parabolic velocity profile, like what's in blue here. Whereas if we're dealing with shear thinning fluids, which are the most commonly non-Newtonian fluids that we experience here at RheoSense, these concentrated polymer solutions, concentrated protein solutions, typically we see shear thinning behavior. And if we look at the wall, which is where our pressure sensors are located, the shear rate in red here that the fluid is experiencing, if it's a shear thinning fluid, is much higher than we expect based on our Newtonian assumption. And so since this shear rate is much higher than expected, we need to make this correction. So, and this is the equation, again, that we use to calculate shear rate. This is assuming Newtonian behavior. And because when we have shear thinning fluids, we no longer have Newtonian behavior, we need to do some quick math to correct the shear rate and thus correct our viscosity measurements. And so go through the WRM correction quickly. So in our system, we calculate the shear stress from the change in pressure that the instrument measures. And since we don't make any assumptions about the material behavior with regard to the shear stress, there is no correction necessary or needed in our instrumentation. However, because our shear rate does make some assumptions about the material in question, we do have to make the correction. And so with the WRM correction, there's different equations that you can use depending on the geometry of your rheometer. And so in our case, we have a rectangular channel. So this is the equation that we use to do the WRM correction. So the gamma dot n, or gamma dot Newtonian, what we calculate before, divided by 3 times 2 plus the derivative of the natural log of the apparent shear rate, gamma dot n, divided by the natural log of the shear stress. And then here, this equation is for a circular channel, like if you have a needle that you're injecting drug into a patient, this is how you would calculate the WRM correction for such a geometry. And so once we correct the shear rate, we can then calculate the true viscosity in the shear thinning region of the graph here. And I do want to make that distinction. You don't need to do the WRM correction here on the Newtonian plateau. You only need to do the WRM correction on the shear thinning region here. And I have an Excel sheet prepped and ready for you guys, and I'll show you how to perform the WRM correction quickly using Excel. So, but to get some of the basics down, what we do is we take the natural log of the shear stress and the natural log of the apparent shear rate, and we plot them and then fit them. In this case, we fit them to a second order polynomial. So typically a quadratic equation like this is sufficient, but if you have a wide range of shear rates that you use, like several decades, like 3, 4, 5 decades of shear rates, you may need to break it up into chunks. And you may also have to play with higher and lower order fits. But the goal is to get an R squared as close to 1 as possible. And so, and I guess a couple more things to look out for. So, like I said before, the shear rate at the wall is much higher than anticipated. And also that means that the viscosity is a little bit lower than anticipated. So when you're going through the correction, some, I guess, pointers to, or hints to help you when you're trying to think about whether or not you're performing the correction properly is you can look and see, you can plot the uncorrected data versus the WRM corrected data. And you should see that the shear rate should be higher than the uncorrected data, and also that the viscosity should be much lower than the uncorrected data. So that'll make more sense as I go through the Excel sheet. So let me pull that up. Let's see. No, all right. So, all right. So here, I can point you guys to the handout section. There should be a file in the handout section of the webinar that says WRM Correction Example Data.xlsx, and there will be 2 sheets. One that the WRM correction has already been performed with some xanthan gum, a very low percentage of xanthan gum, which is a shear thinning fluid, and then a blank one, or not, has data, but no correction has been performed yet on a high concentration of protein called bovine gamma globulin. And I'll walk you through how to perform the WRM correction using this this set of data. But here I have just a complete version of the correction just to show you. So at the viscosity that the instrument measured, and then the shear stress that the fluid experienced in the chip, and then here I took the natural log of that shear stress, and then I have the shear rate, took the natural log of that, and that's plotted here on this chart here. So you can see that I fit this equation or I fit this data to a quadratic equation, which here says it's negative 0.0516 x squared plus 1.63x plus 4.38x. And so what we do is we take the derivative of this equation and then plug in the natural log of the shear stress at each of these points to get this derivative, or get the solution to the derivative. And then we use that equation I mentioned before to get the true shear rate. So that's the shear rate divided by 3 times 2 plus this derivative. So now we get the shear rate, the true shear rate experienced by this fluid. And then, as you can see as a check, the shear rates, the true shear rates are much higher than the apparent shear rate that the instrument gave us when we first performed the experiment. And then we take true shear rate, divide by, or we take the shear stress, divide by the shear rate to get the viscosity. And do make sure that your units are correct, because here shear stress is in pascals, but the true viscosity is in millipascal seconds. So, and that can dramatically alter your viscosity value if you aren't consistent with your units. And so here I have plotted the apparent viscosity data in blue and then the corrected viscosity data in red. And so I'll now step you through how to extract this information and correct your data using the WRM correction. So here, first things first, I exported the data. Oops. I exported the data so that I didn't have shear stress calculated. Depending on your export settings, you can get the instrument to just export the shear stress for you anyway. But sometimes that's not apparent that you can export the shear stress information. So here I have an example of no shear stress exported, just to show you that it's really easy to calculate the shear stress. So I have the shear stress. It's, viscosity is shear stress divided by shear rate, so just multiply. And then don't forget to keep your units consistent. So here we have the shear stresses. Say that in pascals. All right. And so now we'll want to take the natural log of the shear stress. And this is unitless, so take the natural log. And if you can also follow through with me and perform this on your own if you're more of a tactile learner. And so now do the natural log of the shear rate. And then I guess I skipped a step. So first I'm going to plot the uncorrected data. It'll make sense why I'm doing this in a second. So shear stress y-axis or x-axis and viscosity on y. And then, because this looks a little goofy, I'm going to put on a logarithmic scale and adjust the axis. Okay. So this is the uncorrected data, and you can see like the first 3 or 4 points are on the Newtonian plateau, so we don't actually need to perform the correction on that, so I'm just going to delete that. All right, so now I'm going to plot the shear stress and shear rate, the natural log of the shear stress and shear rate. And again, so it's easier to see, I'm going to change the axes. All right. And so in Excel, you can just right-click, add a trend line, and we want a polynomial, second order, display the equation, and then increase the font because that's kind of tiny. All right, so we have our equation now, our fitted equation, and it has an r squared of 1, so pretty good fit. So we can take the derivative of this equation, so that's 2 times 0.0348, and this is times the natural log of shear stress plus 0.6298. So that's the derivative of this equation. So now we just need to calculate this derivative for the shear stresses in the shear thinning region of our data. So Excel, just type that back in. We'll do times this and then plus 0.062. All right, delete that. It's in the way. All right, so some things to note. It doesn't matter if this if there's any negative numbers in the equation, in the fitted equation. It works just fine. If you recall this on this bit of example data, the A in this coefficient was negative, but it still works the same. So don't worry if you have negative numbers, that's fine. Just perform the derivative. And so now that we have the derivative, we can finally do the shear rate correction. All right, so we recall we need to use the apparent shear rate, so the shear rate that the instrument gave us, and then we divide that by 3, and then we multiply that by 2 plus the value of that derivative that we just calculated, and we now have the corrected shear rate. And so as you can see, the shear rates of the correction are a bit larger than the apparent shear rates that we got from the instrument, especially as the shear rate is increased. So like, for instance, this is at 98,000 inverse seconds, but over here, we're at 102,000, almost 103,000 inverse seconds. All right, so now that we have the corrected shear rate, we can now calculate the correct viscosity. So correct viscosity. So again, just shear stress divided by shear rate. So that by this, and then don't forget your units. Make sure it's in millipascal seconds. So we have corrected the viscosity here. Just to make the plotting a little bit easier, I'm going to just copy the original shear rate and viscosity values, the uncorrected ones for the Newtonian plateau, so that when I plot this corrected data, it's easy. So over here, and then the x values here, and then the y values here, and then do oops. just want to show the plot where it's easier to see. And then we'll change this to be, I don't know, like 10. All right, so now, you can see, maybe I'll zoom in a little more. So now you can see here that, so you can see here that the shear rate at the corrected data is larger than the uncorrected data, and that the viscosity is also lower than the uncorrected data. So now we have an accurate representation of our non-Newtonian fluid. So, and with that, that's basically all I had for you guys today. So if there are any questions, feel free to ask them. And thank you. That's you can reach us. You can reach me by email at imam@RheoSensense.com, and you can call us here if you have any questions. You can talk to me or Grace or anyone. We're always happy to help here. So, yeah. So we do have a question. Do all viscometers require the WRM correction for non-Newtonian fluids? The answer is no. It completely depends on the flow that you induce when you're using your viscometer. So the best example of a viscometer that does not require the WRM correction is the cone and plate rheometer. But rheometers that induce inhomogeneous flows like ours, or parallel plates or capillary viscometers, those require the non-Newtonian, or not the WRM correction. So, all right. I guess that was all the questions that we had come in for us today. So I guess this concludes the webinar. Thank you for joining us and listening, and I hope I was able to help you guys out and give you some more tools to help analyze your various fluids that you use for multiple applications. Yeah. So, thank you.